So today at QC Talks, we are very excited to have Andriy Miranskyy from Ryerson University, Toronto in Canada. And he's associate professor at the Department of Computer Science and with a lot of research experience in mitigating risk in software engineering and focusing on large-scale software systems. And he has more than 20 plus years of experience in software engineering, in information management, and pharmaceutical industry, and also he has worked as software developer in IBM. And so with this, I would like to pass to Andriy, who will be talking about quantum computing and software engineering interpenetration.
Thank you very much. Yeah. So thank you very much for inviting me. So yeah, today I wanted to talk about software and quantum computing and how these two things are interconnected. And let's see if I can move to the next slide. So just a couple of words about the lab. So there are roughly 10 of us, grad students and postdocs. And the goal of the lab in general is to mitigate risks in software engineering. And obviously risks change as time goes by, but there's typically always a risk somewhere. And typically this is where a photo of the group members would go from one of our meetings. Unfortunately, due to COVID, we haven't seen each other for more than a year. So instead, here's an aerial view of the campus in Toronto. And the lab works in various areas of software engineering. So we create architectures for processing big data, and then we apply them for large-scale products to do live log telemetry analysis and anomaly detections, doing some testing, maintenance work, things like that. And around 2018, we ventured into quantum computing world, and that will be the core part of this talk. And to kind of tackle the problems in this area through a range of plethora of tools from data mining, machine learning world, HPC, simulation, blockchain, and just wanted to thank our partners at IBM Centre for Advanced Studies for giving us access, for Compute Canada for the HPC resources. All of that helps propel our research forward. So on the quantum computing side, we have this three-pronged approach. So we look at how quantum computing affects existing coding practices for the code that runs on modern computers or classic computers, depending on how you call it, and that's done jointly with IBM. And then we also look at how we as software engineers can help build better code for quantum computers. And recently we ventured in one more little branch / area. We've submitted a paper recently. It's a double-blind review process, so I can't talk about it yet, but hopefully in a month or so, we'll be able to disclose some fun things. So the rest of the talk will structure as follows. So we'll just have a quick refresh of the quantum computing timeline and how this timeline will evolve in the future. And I mean, we don't have a crystal ball, but we can have kind of general understanding of what's going on. And so far, it seems that a lot of these projections are on track. And then we'll dive into specific challenges for legacy code and for quantum programs. So timeline. I deliberately kept this slide frozen in 2018. So I actually used this timeline slide back at the XC19. And you'll see in a minute why I decided to keep it unchanged. So in 1982, Feynman created the field essentially where he said that quantum systems should be computed and simulated using quantum computers rather than classic computers. And then for a number of years, there were a lot of theoretical work, and one of the algorithms that have been introduced in '94 and still causing a lot of excitement or scare, depending on who you ask, was introduced by Shor. And we'll kind of look at Shor's algorithm throughout this talk a number of times at different angles. And then, so the algorithm was introduced amazingly even before the first machine was created. So only 4 years later, the first device was there. So, they froze two atoms and then they measured their state using NMR. And that's how the first machine was born. And then in 2011, the Canadian startup D-Wave, they introduced an adiabatic device. They're not gate-based machines, they're harder to program because of that, and they're specialized for specific use cases, and they're very efficient for these use cases, but it's hard to churn out a generic code. You need a gate-based machine for that. And so the first gate-based machine was introduced by IBM in 2016. And they made it publicly available using cloud interface, so people could play around and upload their code. And then a year later, the 5 qubits turned into 20 and 50 qubit machines. Interestingly, I think they've just recently retired this 20 and 50 qubit machines from their kind of public clouds. And then in 2018, Google introduced the 72 qubit device. And somewhere around kind of late 18, early 19, IBM said, you know what, in 3 years, we'll achieve quantum supremacy, meaning that we'll be able to introduce the code running on a quantum machine such that it would be significantly faster than on a classic machine. So, and at that time I said, okay, so how realistic is it? Given that it took 18 years to go from 2 qubits to 5 and only 2 years from 5 to 72, possible. And then just a few months later, in the fall of 2019, Google came up with an announcement they actually achieved quantum supremacy 2 years earlier than the IBM's forecast using the Sycamore chip of 54 qubits. And that's kind of the device itself. So by that time, we already knew that, okay, quantum computers are real. They may speed up certain use cases, but when is it going to happen? Right? So that takes us into kind of the future forecast, but to do that, we need to refresh a little bit our knowledge on the measurements of performance first. So obviously, the more qubits in a machine, the better. So that is intuitive. But there are also negative factors affecting machines' performance, measurement errors, decoherence, where basically the state can fall apart spontaneously. The connectivity is also an issue because the qubits have to be kind of interconnected with little wires. I mean, it doesn't have to be a wire in reality, but there have to be some interconnectivity, and not all the qubits are interconnected, so that limits what we can and cannot do with these devices. So then obvious question then becomes, all right, so there's lots of factors. Can I somehow reduce dimensionality to a single number, to a single measure? And so IBM came up with this measure called quantum volume, where they take this pros and cons and they combine it into a mathematical formula and it spits a number. And the higher the number, the better. And right now, if I didn't miss any contenders, what we have is Honeywell reached quantum volume of 128 on a machine with 10 physical qubits. And then IBM have gotten 228 to the quantum volume of 128 using a different type of architecture with 27 qubits. And then in December 2020, IonQ, they introduced a new machine with 32 qubits, and they say that they expect that the quantum volume of it will be very, very high, like more than 4 million, because they were able to solve some of the issues related to noise, so they were able to greatly reduce it. Now, there was this kind of press release, and I haven't seen an actual academic paper. I'm sure it's coming, but I mean, that's what I'm just quoting the press release here. And so the IonQ said, look, given this development, chances are we might end up with kind of billions of quantum volume kind of value. So it kind of resembles what we have for classic machines, where we started with flops and now it's like zettaflops, I think, right, for supercomputers. So why don't we try to get rid of some of the zeros and instead introduce a new measure called algorithmic qubit, where essentially it says how many ideal qubits a machine can represent. So those that we have when we're designing an algorithm itself. So they expect that this new machine that they've introduced to qubit one will have an algorithmic qubit size of 22, so kind of 22 ideal qubits. So, okay, so this is the current state of the world. What's going to happen next? So when will we get to machines with thousands, tens of thousands, millions qubits? So this roadmap is from IBM from January 2020. And when we look at this roadmap, we can see that quantum volume of kind of 10,000 will be reached by the end of this decade. Now, peculiarly, they're beating their own projections from last year. So they already said that they're going to introduce a machine with 1,100 qubits in 2023. And typically, quantum volume is greater than the number of physical qubits. So it's going to push this curve further. And even now, they showed that for their latest measurements, when they were able to achieve the quantum volume of 64 and 128, they are already kind of bending this curve to the left. So they will be able to achieve larger quantum volumes faster than they anticipate, assuming that the trend continues, of course. And IonQ has kind of a similar, conceptually similar projections where there's some sort of an exponential growth. Now there's algorithm qubits on the y-axis rather than quantum volume, and they're gonna achieve this 1,000 ideal qubits by late 2020s. So again, we'll see how this goes. So we kind of see that machines are growing, they're growing fast. It's now an engineering problem rather than a kind of conceptual problem. So we just need to reduce the noise, make sure that things are interconnected. And it is a challenging task, but it seems that so far the engineering teams are very successful. Now, interestingly enough, there are different ways of approaching it. So the first machines were and still are the superconducting ones. So those that require large fridges that use liquid helium, and they cool the atoms to a temperature of almost 0 Kelvin. And those machines are obviously expensive. The maintenance is expensive. You need highly qualified personnel to make them work. That's what IBM, Google, and Rigetti are doing. And then there are ion trap devices. And those use lasers and magnets to trap ions, and ions represent qubits in this case. And that's what Honeywell and IonQ are building. And then there's also photonic architecture. So there's a Toronto-based startup, Xanadu. So they have a machine that uses photons as qubits, and those photons travel through the glass tubes. And then there's a sensor at the end that kind of measures the state. So these are some machines that actually physically exist. Now, there's a very good talk by Dr. Cavaro in the QC talks. So there was a lively discussion about various architectures and kind of those for which computers do exist and those that might be instantiated somewhere in the future. So I encourage you to kind of review it if you're interested in this. But the reason I'm bringing the architectures up is because the architecture will dictate how we're going to use these machines. So, so far, it seems that for foreseeable future, we're going to be using quantum computers as a service, right? Be it via public cloud, or maybe if you're an enterprise and you can afford to put this box in your own data center, then it will be private cloud. But we're not going to put them on a desk, right? Or plug it as a card in a computer, like as a GPU card. And it's already happening, right? So IBM have been doing it since 2017 with their Q experience. And then interestingly enough, recently, vendors such as AWS and Azure, they started offering the aggregators, right? So they take computers manufactured by other companies and they offer them as a service with the REST API, and you just get charged for the kind of resources that you've leveraged. So this is a kind of a very interesting initiative as well, of course. So this is already happening at the kind of commercial side of things. And then an interesting question then, all right, so will we ever get to a box on a table, right, or a card? With the cryogenic machines, chance of it is low, right? Because having a helium-based refrigerator in your house probably is a bit expensive. But for ion-based devices, it is possible. So magnets and lasers doesn't require cooling, or significant cooling at least. So IonQ actually hopes to ship a rack-based size machine by 2023, and then they expect to miniaturize it to kind of desktop size by 2025, so just a few years away. And photonic devices, such as the ones that Xanadu builds, can also be miniaturized. They don't require cryogenic cooling for most of the part. Unfortunately, the detector of the photons, it does require cryogenic cooling, but it is more of an engineering problem. So one potentially can create a photonic detector or detector of photons such that it can operate at the room temperature. And if that happens, and when that happens, they'll be able to kind of package it into a kind of small solution. So maybe one day we'll actually have something on the chip. That's probably not going to happen this decade, but it is possible. So we will have this kind of accelerators, right? Like similar to GPUs, graphical units that speed up tensor computations. Will have quantum accelerators that will speed up certain use cases as part of kind of larger software solutions. And so what are those solutions? What are we solving here, right? And again, just a brief refresh. We know that quantum computers will be able to solve problems that fall into the BQP domain. And it's a superset of the polynomial one and a little bit of NP. And some of the p-space problems. It's still a Turing machine, so NP-complete is out of the question. But nevertheless, there's quite a few problems in the p-space that we are interested in, and that may, like if we speed them up, it will help folks in various domains. And when that's going to happen, well, interestingly enough, in quantum chemistry, and this is kind of that initial use case that Feynman have envisioned, they already have published a number of papers on kind of simulating smaller systems and approximating larger systems. And it seems that they are getting some practical benefits, even on the small machines that we have right now. And then, say, in the quant finance world, I was a preprint recently where the author showed that to price a portfolio of financial instruments such that it's actually kind of beneficial to a practitioner, you need 7,500 of this ideal qubits. Say if you would like to break an RSA key of the length of 2048, which is what most of the modern machines use, then you need 20 million noisy qubits, so kind of qubits that modern machines have in less than a day. So there's quite a bit of spectrum here, of course, right? But it seems that for many practical purposes, given the timelines that we just saw, 5 to 10 years is a realistic window when machines will actually be commercially viable. So with that in mind, let us see how does quantum computing affect existing software, and how can we improve the programming of quantum computing systems. And we'll start with the legacy machines. And this is based on the preprint we put in 2019 that kind of made its way through the publishing system, and it was published just a few months ago in IEEE Software. So we already learned that the quantum algorithm can bring existing crypto schemes. But the timeline of when the breakage actually going to happen is somewhat uncertain. So we saw 20 million qubits, right? Well, given that the current machines are just 60, 70, and maybe 1,000 in 2 years, it's long way until we get to that million, right? So why do we care now? Well, it so happens that we can implement a harvest and decrypt attack, which is a very simple concept where I sniff, say, encrypted network packets, so HTTPS traffic. And if I have storage large enough, I can preserve this traffic. And then when machine becomes powerful enough, the quantum computer becomes powerful enough in the future, I'm going to take these stored packets and I'm going to decrypt them. And obviously, most of the stuff that I'm going to harvest is completely useless. Like the photo of a latte on Instagram. I mean, if you decrypt it, good for you, but it doesn't have much practical value. But I'm sure you can imagine sensitive informations that have to be protected for more than a decade, right? And that's where a lot of scare is coming from. And another interesting point here is, so 20 million is the current lowest bound, but it's not an optimal bound. And to put things into perspective, so back in 2012, the researchers came up with an algorithm for breaking this RSA key of size 2048. And at that time, they said, we need 1 billion qubits. And then another group in mid-2016, they came up with a solution that needed only 230 million qubits. And that was lowered to 130 million in early 2019. And then just a few months later, another group combining a lot of clever tricks was able to push it down to 20 million. Right? And so given this dynamics and given that 20 million is not an optimal lower boundary, I'm sure that there are other research groups working on this problem right now. And as time goes by, this number is going to get lower. And computers, on the other hand, are growing, and it seems that a lot of manufacturers are beating their own expectations. So we might get to that point where the decrypt part of the attack will become viable sooner rather than we expect. So what's the solution? Okay, well, we'll need to look at the existing encryption schemes and replace or alter them. And for symmetric encryption, such as AES, right, so that's what's often used to say encrypt data at rest, its nemesis is Grovel's algorithm. So it basically speeds up the brute force attack, and the brute force goes from order of n attempts to order of square root of n attempts. So there, the solution is actually fairly straightforward. So the algorithm itself is safe. We just need to increase the key lengths proportional to the square root of n, and that's going to make the problem go away. The asymmetric encryption is a bit trickier, unfortunately, so such as RSA. So kind of most of the asymmetric stuff these days is based on integer factorization, and Shor's algorithm is going to speed up integer factorizations greatly. So there, to make the software quantum resistant, we do need to replace RSA and similar type of schemes with something quantum resistant. And there are algorithms out there that do it. There's quite a few from the lattice-based family ones. Peculiar, they're actually faster than the integer factorization ones. So, but if you do this replacement, the encryption part of your code might be faster than your current one. But it's still somewhat in flux in terms of what exactly do you need to replace it with. So NIST has been working on standardization for the last few years, and it is expected that by 22, 23, they will come up with the standard and say, okay, this is a 4 algorithms that we recommend. I think now they have 5 contenders left. They started with more than 50. And that applies to legacy and new software. With newer software, we as software engineers can probably imagine that it will be relatively easy, because now we can just design the new software with this issue in mind, and we say, okay, right now, whatever I'm coding, I'm going to plug in RSA, but I'm going to make the design such that I can take the RSA out and I'm going to plug something else in, or maybe I'll just kind of use both of them in parallel, right? Whatever the design goals are. The legacy stuff, though, is a bit more convoluted. And we know very well that making modifications to legacy code is a non-trivial exercise. It doesn't have to be related to security and crypto. I mean, any change to large legacy code base is a pain. This has this eerie resemblance to the Y2K problem of 20 years ago, right? So December 31st at midnight of December 31st of 1999 at midnight, the timers, kind of the ways that were designed, many of them were supposed to kind of roll over and start at time 0. And obviously, this is not something that you wanted to have for a mission critical system, so the system had to be updated. And strategically, everybody understood what has to be done. You just need to take an old timer out, plug a new timer in, and that's straightforward. Tactically, it ended up being a nightmare. Kind of the enterprise software engineers often say nothing is easy, right? Kind of quoting that's Jester Tal, and indeed nothing is easy. Because the code bases were missing, the build systems were not there, the engineers who built that software in the first place were long retired, etc., etc., etc. So we've overcome these challenges, of course, but it was non-trivial. And we might end up in a similar situation now when we need to take kind of this old security code out and plug a new security code in. And so we got together with colleagues at IBM, and we said, "But what is the process that we need to follow to achieve that? And can we learn the lessons from the Y2K problem and kind of port them to the modern one at the conceptual level, of course?" And so we came up with this process where it's 7 steps, and basically you need to get the blessing and support of execs and management, and you need to examine the products and look at the design, redesign with script agility in mind, educate the programmers and designers on the importance of what they have to do, size it, implement, maintain. And so kind of this list we came up with in 2019, and then in 2020 we said, well, let's actually validate that it works. I mean, conceptually it should, but only the actual application of the process will prove it. So for a good chunk of 2020, we had a group that actually was replacing the existing security-related code with a new quantum resilient one in a legacy product. And the process itself works, so that's fine, but the devil is as usual in details. So it ended up being much harder than we anticipated. We are finalizing the report on that, and hopefully we'll release it in the next couple of months. And we hope that some of the things we fall into, like all the traps, they're generic enough that other programmers and software engineers might be able to learn from our endeavor and actually apply it in their use cases. So that's on the kind of legacy software. Now let's move, kind of shift the gear a little bit, and let's move to the quantum programs and see how we can improve the quality of code listings for the actual quantum computers. And that's based on 2 papers from XC19 and XC20. And then this spring, we actually extended it, and there's a preprint on arXiv. And I would recommend kind of looking at that one, because it's really kind of a superset of XC19 and XC20. And I put here the photo of the cryogenic core just because I like the aesthetics, but all of the thoughts here are applicable to any quantum computing architecture, be it ionic or photonic, and the same principles will remain. So as we already said multiple times, quantum computers are becoming more mainstream, so we need to explore how we can improve coding of these machines. And fundamentally, as a community, we would like to explore the practices that we currently have. Can we port them to the world of quantum computing? Are there things that we cannot port, period? And what are the novel practices that should be created to address the challenges? And let's look at this example. So assuming that we're going to be using the quantum machines as a service, right? So the flow will be very similar to what we have on the screen. So essentially, say, here in this toy example, I as a user would like to factorize an integer. I think I'd like to use Shor's algorithm, so I have a large integer, and I'd like to get the factors back. So I'll pass my integer, probably through some sort of web interface or REST API, to the front end of my kind of web app. That's going to pass it to the backend. On the backend, that's where most of the magic is going to happen. That's where I'm going to be invoking the quantum computing code, and probably some sort of form of quantum assembly is going to be sent to the quantum computer itself. And The quantum computer controller is just a basic classic machine, right? It's going to take this quantum assembly and it's going to translate it into some sort of control sequence that goes to the actual core. Then we're going to measure the state of qubits. We'll probably have to do it multiple times, multiple shots. So eventually we're going to take this abstract data and we're going to convert it into the list of factors, those list of numbers, factor integer n, and we're going to propagate it all the way back to the user, right? And you can imagine that the same flow is applicable to other use cases, be it Grover search or some sort of eigenvalue finding for a matrix, et cetera, et cetera. So you pass something in, you get something out. So very kind of functional. How are we going to do it from a practical perspective? Well, depends on the framework. But I think most of the people who develop algorithms in the quantum computing world, those I talk to, they do understand that in order to enable this ecosystem, you need to package the algorithms in such a way that the programmer without any knowledge of quantum computer will be able to use them. And the Qiskit framework, they have a library called Aqua, and that's exactly what they do. So they package popular algorithms as a Python class, and then you just invoke this class, and then the magic happens in the background. So you can probably follow this code even if you've never saw quantum computing listing, but as long as you coded something in Python, right? So all I'm doing here is I'm wrapping my integer factorization task into a function, and there I need to get a pointer to the backend where I'm going to run it. And in this case, I'm just going to use quantum assembly simulator that comes with Qiskit framework. And by the way, to install Qiskit framework, all you need to do is just say pip install Qiskit in your Python environment, and that's it, like you are going to run. In principle, I can replace this backend with a pointer to an actual machine. I'll just need to provide kind of my secret key to get access to it. And then the actual instantiation of the algorithm is trivial. All right, so I have my class called Shore, right? I just have to import it from the Aqua algorithms package. And then I'm going to pass to it my integers I'd like to factorize. That's the end of the story. Algorithm has been instantiated. And then I need to execute it on the backend, and I'm going to get results. And results is just a data structure, and there's an attribute in this data structure called factors, and that factors is just list of the integers, right? So basically, if I'm going to invoke this method, I'm going to get 3 and 5 back. So 3 multiplied by 5 is 15. Great. So I, as a programmer, can leverage quantum computer without knowing much about quantum computing. And that's exactly what we're aiming for. But what if I have a use case such that it's not part of the Aqua library or a similar library? All right, so then I need to implement it myself. And perhaps I actually even found a paper with an algorithm, or maybe I kind of clever enough to build my own algorithm. So I know a lot about kind of quantum computing and physics, and therefore I'm capable of doing that too. So then we go into the world of quantum assembly. And even without knowing what this code is doing, and it's something very trivial here, where we're just measuring a superposition, this feels, as a software engineer, I cringe, right? Because this is second generation language assembly. So we know it is error prone, it will be verbose. So that's a little bit scary. But in practice, though, will we open a notepad and start kind of hacking away the quantum assembly commands? And reality is no. It's actually much better than that, because Sir, Qiskit, kind of other frameworks, they really wrap this low-level quantum assembly code into Python or a similar type of language. So we go from second generation language to the fourth generation language in an instance, and that makes life much easier. And we'll look at the code listing in a sec to kind of make it a bit more quantitative. But fundamentally, right, when you look at software engineering phases, what do we have, right? We need to collect requirements. And if I treat my quantum code as a black box, nothing's changing, right? I can get my specs, I can do the sizing, I can analyze the conflicts, etc. Design, you saw the sequence diagram. It's basic vanilla UML, no changes needed. I can, as long as quantum computer is a black box, there's nothing else I need. Now, if the quantum code becomes white box, then life becomes a bit more interesting. And then we might need specialized extensions to the language. For requirement specification, we need extensions to UML. And a lot of these efforts are documented in the lit review by Dr. Zhao from last year. So I kind of highly encourage you to look at it if you're interested in that. But let's look at the construction part. So let's look at how this Shor's class is actually created. So if we go, so now let's look at GitHub. So this is actually Shor.py file that has the class Shor that we just looked at. So what happens under the hood? And again, if you've never coded anything for quantum computer, but you know Python, you can follow it, right? So you're passing a bunch of parameters. There are default values here. There's even basic assertions for the code that's executed on the classic machine. Say kind of this code snippet, so it gets angles. So for a kind of classic part of the code for initial setup, this you can obviously unit test easily in kind of standalone. Then say this method here is actually defining the quantum circuit. You can see that the quantum circuit is actually defined as yet another class. And then under the hood, I'm actually performing some sort of method P, and I have a for loop that seems to be doing something to the angles of the kind of, I guess, of the block sphere to set the values in the Fourier space. And then I might not know what quantum circuit is, but there's a manual for that, right? So actually, let me just go back for a sec. So all I did is I kind of Googled, quantum circuit, and it's a lengthy manual, which is good. Come on, just want to go to the very top. Here we are. And it's auto-generated, right, from the source code itself, a lot of it. So all of these high-level software engineering tools that we have at our disposal, we can readily leverage. And if I'd like to learn what the method P is doing, kind of it points you to this page, and it says that it's going to change the phase gate, and I can look in the psychology the parameters that I'm passing, and this is really just a matrix that I'm setting up. So I can quickly wrap my head around what's going on. I don't really need to look at the low-level kind of gate operations in many cases to understand what's going on. And obviously, you know, when I have this type of for loops and I have the modules and classes, the error proneness of the code goes down dramatically. And this is true for classic machines. This is, of course, true for quantum computers. So what we're dealing with is really more of a scientific computing rather than kind of low-level programming of the 1960s. So I'm kind of starting to run out of time. So let me just touch quickly on testing and maintenance of such a code, and then we'll kind of have more discussion in the Q&A. So on the black box testing phase, you can take the UML diagram and requirements, and you can create your test plans out of it, no problem. And you can create automatic test cases. And you saw it's just a Python listing, so you can use unit test harnesses. You can mock a lot of kind of endpoints for this quantum backend. So all of it can be done with existing code. Now, when we start looking at the verification, the outputs and inputs and the code coverage, life becomes a bit more complicated. And just a previous talk by Dr. Ali, I have talked about the inputs, output, and code coverage, and that there are issues that as you scale the size of the input and the size of the output, life becomes a bit more complex. So I highly encourage you to kind of double check it if you haven't seen the talk yet. So on a simulator, we will be limited. And we do want to run things on the quantum machine. But quantum machines may introduce their own errors, right? Maybe the hardware problem, it may be the compiler problem. So ideally, you want to take the same piece of code, you want to run it on multiple quantum computers, preferably different architectures, right? Or at least different manufacturers, so that you get rid of the potential fundamental errors in the design. And if you get similar results, you're probably okay. Now, obviously, you're going to say, look, I mean, I'm not going to run in parallel and code up, 2 or 3 different versions of the same code, like one in Circ, one in Qiskit, another one in some other language, like Q#. The good thing is there are already converters that start to emerge, and an example is Penny which Xanadu hosts, and it is capable of kind of taking taking input in one language and kind of translating it into a different language automatically, right? Similar to how we had, say, C to Fortran translators a while ago, right? So you can actually simplify this process, right? You don't really need to do things manually. On the validation side of, we got some numbers, but are they right, right? That really depends on the complexity of the validation. Because if I have something like integer factorization, then validation is trivial. I just need to kind of multiply all the numbers together. If I get my input, I'm good. I've validated my output. But if I have something a bit more esoteric, like boson sampling, where I'm going to get something out, but in order to verify if it's correct, it's actually an X complexity process. So there are various tricks that people try to employ. There's some machine learning approximations, but this one is a hard problem to tackle. And this is something that you kind of have to deal with on a case-by-case basis. On the white boxing side, so we saw the code listing on GitHub, right? I can create issues, I can do code reviews, I can do code inspections. All of the power of the modern tools is available to us. We can do automatic linting too. Even like say when I write code for Qiskit and PyCharm, it already picks up on some of the Python related issues and it yells at me. And there may be specialized kind of anti-patterns, I guess, right? So say, for example, in QC 2021, there will be a paper presented. There's already a preprint out where they identified a number of those anti-patterns. You can codify them in a linter, and it will say, look, don't do this because there is an issue. So we can definitely implement a lot of these things. Interactive debugging is hard, though. So for most interactive debugging is impossible in an actual machine. On a simulator, actually, we can do a lot of things, but then scalability problem kicks in. So superposition, entanglement, node loading are our nemesis, but there are some use cases that can be exploited and automatically detected. And there we can do a debugging on a real machine. And we looked in the papers on, say, entanglement and separability. So you can measure entangled qubits. But if you can separate groups of qubits, then you can measure kind of parts of the parts of the registry without disturbing the rest of them. We can't really clone any qubit, but if they're mutually orthogonal states, we can do that. We are allowed to do it. So say in this case, I'm cloning states of Q0 and Q1 into Q2 and Q3. So this is the things that we may potentially exploit in the future, and it can be done automatically, right? So the static analyzer of the code will look and say, oh, this is something that we can actually debug. So I can kind of tell through the IDE to the developer, look, I mean, this type of code I can debug, I can exploit, and this is something that potentially can be leveraged. And there's kind of one more minute with kind of mapping of the test phases, right? Can acceptance testing we can definitely do. We show to the user, say, is it good? Integration testing is a black box we can do. Unit functional system testing becomes a little bit more convoluted and philosophical. If you're interested in this type of kind of categorization and mapping, take a look at the preprint. We chat about it. So this kind of brings me to the end. So we looked at the timeline and the forecast in terms of how quantum computers evolve and how that affects us as software engineers, be it for maintainers of the existing software or be it for developers of the quantum software. In short, this is a field where there's lots of new problems and low-hanging fruits, and the community is growing. And I encourage you to join. I mean, I suspect I'm preaching to the converted here. Obviously, the people listening to this talks are already interested in the field. But if you want to chat with me, just give me a shout. The COVID brought a lot of problems, but at least the virtualization is a benefit. So I'll be happy to have a discussion with you on any topic of interest. So thank you very much for your time.
Thank you very much, Andriy. So I think we have first question from Rui. So I think since you can unmute yourself, so you may ask directly.
Yeah, thank you, Andrew. I think it was very interesting talk. So one of the things about using this as a service, quantum programs as a service, I think it will come from the fact that eventually we will have to know what to send to the quantum computer and what to send to the classical ones, right? So I don't know if you have any thoughts on how to do that, how to split computation across, classical and quantum, right?
And I don't have a crystal ball, but I have a feeling that we'll repeat a process that we've done for GPUs, right? So say we'll have frameworks similar to TensorFlow that will say, oh, there is a GPU available. Let me kind of split my machine learning algorithm into low-level pieces. Oh, this piece actually can be better computed on GPU, and this can be better computed on the CPU. And sometimes the TensorFlow optimizer actually estimates incorrectly, and it shouldn't go to GPU, but it's still sensitive. And there's already a quantum version of TensorFlow, right? And they're actually kind of trying to mimic exactly this principle where it's let's estimate how much it's going to take on this versus that and send it accordingly. So probably that would be the way for the foreseeable future.
Yeah, thanks. That's right.
So let's see if we have any question, not on the Zoom. So, but yeah, I have one question. So I think since we work a bit with now on testing, so the big challenge we are facing right now is that which benchmarks to use for testing, and reviewers are giving us a lot of these comments, and most of the programs we use, they are not big, and this is a typical comment we're getting that, you tested these benchmarks, but these are from the books, or these are these Shor's algorithms, so we don't have big programs. So, but I don't know actually, what do you think? If I have to write a testing paper, what is,
Well, it's similar to the MSR reviewer who says, "Oh, you've tested your idea on 5 code bases, so it should have been 50 million, right? You could have gone to GitHub and harvested the whole GitHub." Right? So and everybody has their own sweet number, right? And it's an interesting issue that I think we as a community face. And this actually maps to some of the discussion we had on the unit test versus functional test versus system test. Because when we first tackled it, it was like, oh, this is simple, right? Okay, unit test, it's a function. But then once I get to a specific function, like functional test, so get the specific requirement versus system as a whole, it actually becomes very blurry. Because really what we're building right now is scientific computing boxes, right? So I have Shor's, I have Grover, and this is a use case as a whole. Like my output is, I just need the numbers out. That's it. I'm going to stop the code right there. So I think as an argument as a reviewer, you can say, yes, hypothetically, the problem can be big, but the small one is what a lot of people care about in the first place. So why not use it as a reference point? It's actually a very interesting question. Can we build a reference library? And maybe we can take Qiskit Aqua or similar type of library, pick up a few representative algorithms, right? Because this is obviously something that the quantum computing community deems relevant and important, and use those. And there's now probably more than 24 of them in Aqua, so we don't need all 20, but pick 5, 3, whatever, right? As a starting point, maybe we use that. That becomes the test bed, and it's actually a very interesting project.
Yeah, I think I'm thinking about that actually a bit. That if we're going to push this research in testing, somehow we need to build this not only the benchmarks but also this like bug repositories, because for example in our paper we generated all the possible mutants, which is not good, it doesn't make sense. And then what could be like the good fault that programmers do in the circuit when they're making the circuit. So it's not still, I tried to look a lot, but I couldn't. But so if we have some sort of this, I guess, repository, we could benefit a lot in this testing research actually.
Yeah, I completely agree. And so some of the anti-patterns, like Dr. Zhao's paper in QC 2021, they identified a few. Obviously, this is not an exhaustive set, and I mean, I'm sure that it's impossible to actually get to a complete set in this universe. But yeah, probably reaching out to some quantum programmers and kind of identifying some may be also an option. And we talked to some folks kind of more on the physics/math side who do code, and there are certain things that they trip on. I don't know how frequently, frankly, right? But they do mention things. So there are certain pain points that they know of and they experience. And as of now, it's more of a folklore, but maybe we can try to quantify it and have kind of quantitative/qualitative research where, okay, let's survey the developers and ask them what the pain points are, and kind of that's the qualitative part, and then we can go back to the quantitative and kind of combining the two. That would be kind of cool too.
All right, thanks, Andrei. So let me see if we got any more questions. Not on the Zoom. Yeah, so if
also no questions on YouTube.
Okay, then I think, yeah, we're a little bit over the time, but I think that was the point to have finished within an hour. So we still have a few minutes if someone has any suggestion or discussion point for Andrei here. Okay, if not, then I would like to thank you very much for your interesting talk and the discussion. And we hope to talk to you soon on some platform.
Yes, thank you very much for the invite once again. It was great seeing everybody, and have a fantastic summer.
Yes,
Thank you very much, Andrei.
Thank you. Bye.